Hi, Judy. All right, let's go on over and see what we have here. Today we have the Celestron CGX-L mount, and we're running the 8-inch Ritchie-Chrétien telescope off of it. It's all polar aligned and locked in to within probably about 5 arc seconds, so we've got an excellent polar alignment tonight. I'm guiding, and we're taking 3-minute images. Now, tonight we're using a monochrome camera, so the images are all going to be in black and white. Judy saw this a little bit yesterday, but I decided to come on out and just demonstrate a couple of things that this mount can do. So, without further ado, let me go take my ugly face off of this, and we'll get over to the telescope. Had a little problem with the computer this evening. I dozed off in the chair tonight and fell asleep, and for some reason the computer ran its battery down. So I've got a little bit of a power issue. I was just able to get the battery charged enough to start broadcasting, but it looks like the stream's running a little bit rough because of the power issue. But it should even out here pretty quick. So the first thing that we're looking at right here is this what's called PhD2 guiding. Now the way guiding works is generally on telescopes you have a small telescope that's set off to the side of it that's got a much shorter focal length. Missy got a new bell on her collar in case you can't hear it. But there's this small telescope on the side of a telescope that's called a guide scope. And that is more or less lined up with the main tube, but it doesn't have to be exactly lined up with the center, the center of the main optical tube and the center of the guide scope don't have to be exact. They just have to be relatively close. So then you hook a camera up to that and you start taking images. And you see up here on the left side, you'll see the image that the guide scope is seeing. You see there are 2 bright stars right here. And there's a number of other dimmer stars. Now, one of these stars has got a box around it and a set of crosshairs. That's the guide star that we're using. That's the star that the telescope or the program decided was the best fit to be a guide star. Now, the stars that are in circles right here are calibration or reference stars. So what they're doing is they're looking at the relationship between these stars and that guide star. Now, if you look down here at the bottom, you'll see there's kind of a dotted line right here in the middle between the red and the blue lines. That is where the telescope would normally just be guiding on its own, just the mount itself. As you turn the tracking on the mount, it would want to follow that dotted line right here in the middle. Now, if you look at these 2 lines on either side of it, these are small corrections that are being made in declination and right ascension by PhD2 to keep that guide star locked directly in the crosshairs. And as you see, we've got a very tight pattern where that guide star is being held very tightly in the crosshairs. It's a little bit high tonight for some reason, but normally it's all within this center circle. But it's still a very good pattern right here. And as a result of that, when we take images, we see something that looks like this. Now, initially, this is what the raw view on the telescope looks like. And then what we do is we stretch it to maximize the amount of data that's on the screen. So here's the data that's coming in. This is the light data coming in from the telescope. And you notice from about here out, there's really not much. So rather than look at this entire range of images, when we stretch it, it brings it all in a little bit tighter. And it gets the most data on the screen. So if we bring that over like that, that'll be the white end. This is the black end, and then this middle one here is the mid-range. So you see the black end. If we bring this down a little bit, the background gets a little lighter. We want a nice black background, so we want to get that right up tight against that peak. And then we bring the mid-range in, or the midtones, till we get a little bit more detail in the galaxy itself. And there we go. This is about 15 minutes worth of exposures. And they're all stacked one on top of the other. And if you want to look at that a little bit closer, here's what the telescope is seeing now. Now, one thing that you may notice is you see how nice and uniform black the background is in space? That's because we're using something called flats and darks tonight. The way you take a dark is you put the lens cap on the telescope and you take however many images you wish of whatever duration you intend to use. So tonight I planned on shooting 3-minute images. So I took 10 3-minute images with the camera with the lens cap on. And what that does is that identifies any what we call hot pixels or any defects in the sensor. And it minimizes those. So we get a nice uniform black, background that is black. Then what you do is you basically put a white light in front of the telescope. You take the cap off and you put a white light. Sometimes you'll put a white t-shirt with a rubber band around it. Or in my case, I just have a light board that I put that covers the entire aperture of the telescope. And then I take 1,000 or so very short exposures. And what that does is it takes care of any vignetting that we would see on the camera. Sometimes, like an old-timey photograph, you'll see dark edges out here in the corners. And all of the data is kind of centralized in the center. This evens it all out. It also removes any dust motes or any defects that are on the sensor itself. And as a result, we get a very stark black background, and we get very even images all over. So let me come on over here to the chat real quick and see if you've got any questions so far. Well, let's see. Yeah, it's buffeting a little bit. Is it starting to calm down some? Like I said, the battery on this thing was extremely, well, it ran out. And, you know, I'm trying to get some battery in and stream at the same time. So I'm on kind of like a low power mode right now. And as a result, I don't have quite as much in the processor department until it charges up a little bit. Okay, so NS Sherlock, where have you been, Bob? Well, I've been doing stuff like this. You know, as you know, I kind of hurt myself back in February, and I kind of stopped making videos for a little while because I couldn't breathe very well with the broken ribs. And I couldn't talk properly. So I just kind of got out of the habit of making videos there for a while, and then I got occupied with some other things. I started working a lot more with the telescope over the summer. I got my ham radio license. You know, so I went and took my test in June. I was able to not only pass the technician test, I was able to pass the general level test as well. Now, next June, I'll go ahead and take what they call the amateur advanced level license, which is also called the golden ticket. And that's the highest level of amateur radio you have. So I set up my radio station. I've got a really nice ham radio right now. I've got an ICOM 7300 and got an antenna tuner for it. And I've got a linear amplifier that boosts my signal from 100 watts up to the legal max of 1,500 watts. And I generally run probably around 800 watts of signal. And I talk to people all the time in Colorado and Florida and Louisiana, out in Pennsylvania and New Jersey. And we'll be doing a little bit of work with that in the future too. Now, you may notice over on Research Flat Moon, I've got the Radio Jove program going. That's using some of the antennas on my roof. My wife says our house is now looking like a Soviet trawler because I've got antennas all over the place. But I'm picking up sunspot activity and radio storms from Jupiter and broadcasting them live. So if you go over to Research Flat Moon, that's where the test broadcast is right now. Eventually, that'll be over here on this channel because this is more of the astronomy channel. But that's basically what I've been doing. Now, let's get back to what we were looking at here in the images. So, this is the Whirlpool Galaxy, or M51. Now, this is the main galaxy right here. There's a sister galaxy next to it that's being affected gravitationally by the Whirlpool Galaxy. Now, you'll notice that this image is in black and white. That's because I'm using a black and white camera. Now, with a one-shot color camera, such as my ZWO-294 MC, which is the camera that Wolfie donated to the channel back when I first started with a telescope, that has groups of 4 pixels. So if you were to imagine a checkerboard arrangement with a 2x2 grid on it. Now, 2 of those pixels in opposite corners are going to be green pixels. The other corner is going to be a red pixel, and the final corner will be a blue pixel. And as a result, when you look at an image, each pixel on that image is a combination of 4 pixels on the camera, with two green sensors and a red and a blue sensor. And depending on what color light hits that grid of 4 pixels will determine how much of the red, blue, and green come out. And that's basically the way a color television works. The problem that you run into is that you decrease your detail by a factor of 4 because you're combining 4 pixels into one, essentially. Now, with a black and white camera, every single picture or pixel is either on or off. It's black or it's white. And as a result, you get 4 times the detail. And because of that, most astronomers tend to use these monochrome cameras, these black and white cameras, because there's so much more detail in them. Now, the way you generate a color image from this is you take an hour's worth of images with the monochrome camera looking through a red filter. Then you take another hour through a blue filter, and finally a third hour through a green filter. And then you take those 3 images, those 3 stacked images, you put them into Photoshop, you white balance them, and you combine them, and you end up with a color photograph. Now, that seems like a lot of work, but one of the things that you can do with it is you don't have to use red, blue, and green filters. So what we typically use are what are called narrowband filters. So I'll have a filter that just looks at light emitted from hydrogen gas, and another one that looks at light emitted from oxygen, and a third one that looks at light emitted from sulfur. And if you look at an object like the Whirlpool Galaxy right here, they'll look very different in each of those bands. And then what you do is you artificially color those bands. So for example, you'll map hydrogen to red, and you'll map sulfur to green and oxygen to blue, say. Don't quote me on those, but I know hydrogen is red, and I may have the other 2 backwards, but you get the idea. And as a result, you get a very detailed color picture, and that's what's called the Hubble palette. And that's where the images from Hubble come from. Telescopes like Hubble that look in the visual frequencies or wavelengths generally are black and white cameras like this one, but they have a series of filters that they shoot the images through, and then they combine them. And that's where you get these beautiful Hubble images, and I'll be able to take images similar to that. Now, when you look at this image of the Whirlpool Galaxy here on the screen, the zoom on this is in auto. And the reason that it's in auto is that you want the entire image to appear on the screen. However, this is not the magnification of the telescope. The magnification of the telescope is 100%. So let me show you what the telescope is actually looking at. That's what the telescope is looking at. So as you can see, there's really quite a bit of magnification in this 8-inch Ritchie-Chrétien telescope. Now the cool thing about it, well, those stars are a little bit oval shaped. I don't like that. Guiding's not perfect on this, it looks like. But you'll notice a very faint line right here. That's a satellite trail. And then you'll see the dust lanes in the galaxy itself. You'll see stars that are between the galaxy and us. I don't recall how far the Whirlpool galaxy is from us. It's actually quite a ways. It's much farther than Andromeda, for example. I'm going to drop this down to 50% if it's all right. But notice the gas clouds that are out here. You can see very faint gas clouds. Now, that's where the narrowband filters come into play, because these gas clouds may be coming from hydrogen, for example, and they'll light up red and give a very nice image. But look at the amount of detail that you get in the galaxy. You see all these little dust lanes? Just amazing stuff. Much nicer than I've been able to get in the past. And the reason that this image is so impressive right now is the fact that I can take very long exposures with this mount. I've got a Celestron CGX-L mount. It's got a capacity of 75 pounds, and it's what's called a German equatorial mount. And this literally tracks the stars. And then with the guiding, it narrows in on that tracking a little bit as well. And as a result, you get these nice, clear images. So let's get back over here to chat and see what's going on. Well, we got a couple of viewers here, one like, but it doesn't look like anybody has any questions right now. Danny Jones, Hoax Police, came in and said hi. So you guys have any questions right now? Kind of see if there's anything in the chat real quick. We'll take a few more images of that, but in the meantime, I think what I'm going to do is let's go over and have a look at Radio Jove real quick. This is Radio Jove. Now what this is a sweep of the radio spectrum between about 16 kilohertz, and it goes up to a little over 24 kilohertz. Now, this kind of bright band right in here, in these bands, these have to do with the resonance of my antenna, and that's just an artifact. Now, occasionally you'll see horizontal streaks like this. Here's another one right here. These are radio broadcasts in the shortwave frequencies. This is about, looks like about 18 megahertz is where these are. Here's a couple more down here. Now, when you look at this, what you're looking for is you're looking for long, feathery, vertical patterns that are kind of this color right here, this real light green color. Because those are the radio storms from Jupiter, which kind of look like teeth, you know, like a series of sharp lines. See, like these little lines right here, except you'll get a whole series of them. And the solar bursts are kind of like long tongues of that light green color, kind of very feathery looking. Now, looking over here, the radio storms on Jupiter have to do primarily with the orbit of Io around Jupiter. And there are certain positions of Io in relationship to the Earth and Jupiter that tend to pop out these radio bursts. And they've been followed for 80 years now. And as a result, statistically, we can say that, well, here's the Io A. You know, the arrangement of Io, Jupiter, and the Earth yields a lot of radio outbursts in this position here. This is the IOC, and down here is IOB. This little brown dot down here is Jupiter, and it follows along in this path like so. So as it goes through this, we'll expect to have some outbursts from Jupiter as it comes through right here. Now, if you look down at the bottom, you see Jupiter is above the horizon right now. It's in the southeast. Well, it's actually almost due east of me. This is 90 degrees right here. And it's a little past 90 degrees towards the south. Here's 180 over here. So this is Jupiter, and it's rising right now. It'll peak up here, probably around 3 o'clock in the morning for me, and then it'll start going down again. And then tomorrow, the sun will rise on this outer arc. So when Jupiter's up, we look for Jupiter radio transmissions, especially as it goes through these red areas and the green areas. And during the day, as the sun comes up, we'll start seeing some solar activity out on this tracing. This is just one of those things that, you kind of got to catch it when it happens. You generally, we kind of get a good idea of when the Jupiter activity is going to be based on these little areas here. However, solar activity is a lot more random. As long as the sun is up, you can always have an ejection event, a solar flare or a coronal ejection. It'll pop out and we'll get some radio signals from that. You can also get flares of the aurora and other effects of what they call space weather. So let's go see what we've got over here. Rodin's here. How you doing? Yeah, an X-class solar flare. Solar flares are graded according to the alphabet, and X is extremely high in the alphabet. That is something that will actually start causing issues with electrical transmission grids. An X-class solar flare can disrupt radio communications. It can disrupt power grids. Now, obviously, we've known about these for a long time, and we do have precautions. We do have some shielding in place. But that's actually one of the reasons that they're testing Artemis this weekend. They're sending it to the moon without a crew because one of the things they're doing is they're testing different types of radiation shielding, because in our atmosphere, or on Earth here, we have a magnetic field around the Earth. And that magnetic field acts as a buffer between the solar wind, the radiation from the solar wind, and the Earth. That causes the solar wind to kind of go around us like a sailboat cutting through the water. Now, when we're out in deep space, we don't have that magnetic field protecting us anymore, and as a result, the solar wind goes right through the Orion capsule at a velocity between 300 and 700 kilometers a second. And it exposes the occupants of that capsule to radiation. So if we get a really bad solar flare, they've got to have some way of shielding the astronauts to protect them a little bit. They may not be able to protect them completely, but, you don't just basically stick somebody in a microwave oven and turn it on and say, hey, best of luck to you. Yeah, we're right now at a solar minima, so we're not getting a lot of activity with the sun. That doesn't mean it won't happen. It just means that the sun right now is actually kind of boring, not seeing a whole lot. So in any event, that's just a little brief explanation. This is running right now over on Research Flat Moon, and it's been running for days now. I was basically testing the calibration of the output here, and I was also testing the stability of the stream, and it really seems to be doing well. So let's go back to our other images. Yeah, there we go. That's looking pretty good. Oh, come on. Is that frozen up on me? Let me go on out and see if that froze up on me real quick. But in any event, there's the Whirlpool Galaxy starting to come together very, very nicely. I'm going to go on mute here for a minute. I'm just going to go on out and check the telescope real quick. Actually, specifically, check the computer that is running the telescope. I'm going to turn it off. Okay, I just had to go on out and kind of give it the evil eye for a minute. Now it seems to be working a little better. It knows who's boss now. So here's our tracking. As you see, our tracking is still maintaining very nicely, and we're getting nice patterns right here in the center. And the result of that are these beautiful images that we're getting. Now, I'm going to show you a different program that I use right here. This is called Sky Tracker. And it does some very interesting things. So for example, if you go over here to this thing called TLE files, and you put in GPS satellites, and download the TLE file. That is the two-line element. That is the Keplerian orbital elements for each of the satellites. And what you can do with that is that will tell you, given your time and your location, exactly where to point your telescope to look at one of these satellites. So what we're going to do right now is I'm going to go ahead and stop tracking. And we've gotten some very nice images here. And there you go with that. So what we'll do is we'll stop live stacking of that. We'll just go ahead and save it real quick. Close it down, turn that off. Now, the other thing that I'm going to do is I'm going to decrease my exposure time from 180 seconds down to about 8. See, here's the center of the Whirlpool galaxy, and here's its sister galaxy right here. That's the galactic centers. Let's go ahead and put this on to automatic. And we're going to stretch it a little bit here so that we can see it. So you see here's the galaxies. And this is only an 8-second exposure. But you can clearly make out where those galaxies are. But what I'm going to do right now is I'm going to go over and see whether or not I can find a I'm going to go try and find a GPS satellite. So here are the GPS satellites. Now here's one satellite that's way down on the horizon. We don't really want that one. That one's getting a little better. This one's actually not too far from us, right there. Let's go ahead and have a look at that one, see if we can spot it. So now this program is taking over the mount. And as you see in the background, it's moving the mount right now. And what it's doing is it's going to try and lock in on that satellite. And what you'll see is the satellite will be still, but the stars will be moving in the background. Let's see if we can spot one. And there it is right there, I think. So you see these are stars, and there is a little GPS satellite right there. Now notice that that's a little bit streaked, so my tracking is off just a hair. Let me see what happens with this. Yeah, it didn't help. This should bring it back into the field. I'm thinking that the tracking on this mount is just a hair off. The polar alignment should be really good. And that should be a round dot right there. But as you see, it's a slight streak. GPS satellites actually move as opposed to geosynchronous satellites that don't. So I'll show you a couple of geosynchronous satellites. First, we're going to have to disconnect the mount, turn off continuous tracking, and reconnect the mount. Then we're going to go back over here to the TLE file, and we're going to go to geostationary satellites, download that file. Boy, the dogs are just talking tonight. This is Amazonas 5, and here's the satellite right here, and it's located right here over the Amazon. So let's see if we can go over there and see if we can spot it. So the mount is slewing a little bit right now. Guys, stop it. The red circle is where the telescope is pointing, and the blue dot is where the satellite is. So it'll go over to it, and then it'll lock onto it, and that circle will turn green. There we go. I'll give it just a second. Let's see if we've got some satellites. There they are. These are the satellites right here. Tell you what, I'm going to see if I can bring these up a little bit more. Trying to adjust the timing a little bit here. So this is a group of 3 geostationary satellites. Now there's a couple more down below that are outside of our field of view here. But that's what a satellite looks like through a telescope. These streaks, of course, are the stars. And See if we can bring this up a little bit more. Now we're taking shorter exposures. You see the stars are going by as the satellites are themselves are in orbit moving in this direction, so the stars appear to move in the opposite direction. It's pretty cool, isn't it? Let's go back over to chat. Artemis does have radiation detectors for this upcoming lunar test. Yes, it's got 54,000 of them. It has 3 mannequins in it. One is fully suited up in the command position. That is a male mannequin. And then they have 2 female mannequins in there as well. One of them is Zoland, I think her name is. And she is wearing a vest designed by the Israelis, designed specifically to protect the breasts and internal organs of women. It's kind of like an armored vest, you know, like you would see in body armor. It's a rather thick bit of material, and it covers the torso. The other one, and I'm sorry if I for some reason I can't remember her name, but she's basically just wearing a shirt. And she is the control without any protection, and they've got sensors all over them, and they're looking at the different amounts of radiation that the different body parts hit. So it's pretty cool. Now, there is something that's very interesting in this program, and that is that you can go right here. Let me pull it up again. Under astronomical objects, you'll see something over here called JPL. These are spacecraft and satellites that are in flight now. Now, in a few days, we're actually going to be able to go over, and we'll be able to pull up Artemis. I don't know if they've got it in here yet. Yep, looks like. So right there, we'll be able to pull up the orbital elements of the Artemis spacecraft when it launches. And these will be updated very frequently. So the bottom line is we're going to try and image Artemis on the way to the moon and the way back from the moon. There's going to be a point that we won't be able to see it any longer because it's too far away, or it's on the far side of the moon. However, I was attempting to image the James Webb Space Telescope the other day, which is 1.5 million miles away, well beyond the orbit of the moon, out at L2. And unfortunately, I missed it in the field of view, but that's one of my projects tonight when I get done with this. I'm going to try and I'm going to go ahead and try and image the James Webb Space Telescope, and that'll be a test for Artemis later on in the week. But it should be kind of cool because we should be able to actually see it in flight. At least that's my goal. Now, let's go back over here and just, with these short exposures, let me see what the GPS satellites look like. So we'll download that imaging file again. I'm going to go ahead and disconnect the mount, put it back on to continuous tracking, and reconnect it. Now look at that. See the satellites going through? And the stars are fixed. Those are satellites in flight around the Earth and geostationary orbit. Notice the stars are fixed now, and it's the satellites that are moving. That's kind of cool, actually. That might make a nice live stream. Just put it up on the celestial or on the celestial equator, and look at these geostationary satellites in orbit, and you'll be able to see them go by. I'm surprised we don't see the trailers yet. Let's see if the trailers come through. But that's freaking awesome, isn't it? This is from my backyard. Yeah, the male is named Commander Munikin Campos. Now, Munikin, because he's going to the moon, and Campos is named after a guy that I think he was the one that figured out how to connect the carbon dioxide scrubbers from the lunar lander to the command module on that ill-fated Apollo 13 mission. I think that guy was an engineer by the name of Campos. Yeah, lucky mannequin. He's up there. He's up there in space alone with he's up there in space for 42 days with 2 women. That ought to be a pretty cool job to have. Yeah, here they are. See the 2 follow-up? There's 3 of them. I know there's at least 2. But here are a couple more geostationary satellites going by. See them? It's pretty awesome, isn't it? This is from my backyard in Michigan. This is equipment that anybody can have. I've got some really good sponsors that have helped me get some really nice equipment together here. And really putting together quite a nice little observatory. And there's the 3rd one right there, see? But that's what a geostationary satellite looks like. Now compare that to one that's actually not geostationary, but a GPS satellite actually moves around a little bit. So let's go have a look at some geostationary satellite, or some GPS satellites. So let's see. Let's find one that's in a good view. I'm thinking that one's pretty much near it. We're already pretty close to that one. Yeah, there we go. Let's go see if we see anything here. Take a little longer image and see if we can do it. Trying to hit a moving satellite with a telescope is really rather challenging. The problem that you run into is the telescope that I'm using right now is an 8-inch Ritchie Crayon with a focal length of around 1960. There it is right there, down at the bottom. You see it going sideways a little? But the focal length on this telescope and the magnification on it is so great that unless you're right on it, it's very easy to miss. To image satellites, especially moving satellites or the ISS, it's a lot easier with a smaller telescope with a shorter focal length, such as my 80mm refractor. And one of the things that we're going to be doing here soon is I've got a C11 coming, a Celestron 11-inch Schmidt-Cassegrain, and I'm going to put something called Hyperstar on it. Now, that's going to take, the baseline telescope has got a focal length of about 2,800 millimeters, and it is an f10 telescope. If you put this hyperstar on it, you reduce the focal length from 2,800 down to about 600, and you decrease it from f10 down to about f2, so it becomes a very fast, wide field telescope with an enormous light collection area. That is going to be the telescope that I'm going to use to look at satellites and objects in space, and I'll be using it for asteroid surveys as well. This is a really good one for asteroid surveys because it's got a moderate focal length. The other thing with the Ritchey-Chrétien design, there is no corrector plate at the end of it to fog up when it gets dewy at night. That's a problem that you run into with the Schmidt-Cassegrains, is they tend to dew up very quickly. Yeah, Arturo Campos, electrical engineer on Apollo. He did something specific with it. Oh, the power down and power up of the equipment. All right, so I knew he was involved in Apollo 13, and I knew he was one of the people, I think he's the guy that designed the power-up sequence so that they didn't blow, you know, based on what limited power they still had, they didn't blow their circuits. And they were able to power up the module. Yeah, I'm not seeing anything too well here. Let's check this one here and see whether or not maybe this might do it. Let's have a look at another GPS satellite. This one here is a little bit more towards the north, it looks like. See if we can zero in on it a little bit. They're real tough to spot in a telescope. On this particular telescope, it's just too much power for it. You know, it's really good with the moon. It's really good with deep sky objects and galaxies. You can't see all of Andromeda with this. And that, you know, it's just, Andromeda is 5 times the width of the moon. It's just too big. Wait a minute, here we got one. There's the GPS satellite right there. In the center here. For those of you that can't see the cursor, let me bring this over here. You see the corner of the box right there? The upper left corner? The GPS satellite is just off the upper left corner. You see it? That's a real nice view of it. That one we can see very nicely. Notice it's not even streaked. Let's take a little shorter exposures. Bring it down to half a second. There, you see it? Tiny little thing, isn't it? You can clearly see it stationary against the moving stellar background. That's a satellite in orbit right now. Just amazes me what you can do with these things. Now, one of my goals is to try and image the ISS as it goes overhead. That's a lot more challenging than doing this, because this is a GPS satellite, so it's not completely stationary over a spot on the Earth, but it doesn't move very fast relative to, you know, it's faster than a GPS satellite, it's faster than a geosynchronous satellite would be, but it's a lot slower than a low Earth orbit satellite. Let's see if we can have a look at a couple low Earth orbit satellites real quick. So we'll go back up here to the TLE file. We'll look at 100 brightest satellites. Download that file. There, now we just stopped tracking. You see the satellite going by? Now it's following the stars rather than the satellite. See where this one is? No, that's not going to be a good one. It's right on the horizon. The ones that are in pink are not visible. What I want to get is one that's up towards the zenith. They're all down on the horizon right now, unfortunately. That one's a possibility. Let's see if we can see that one. That guy's right there. Still waiting on the plaque for the observatory platform. That is going to be the Junie Bassett Observatory at Shamrock Banks. She donated a lot of the funding for it, and it's going to be dedicated to her. She's a great supporter of the channel. Okay, so that satellite ought to be here, but it's not really helping me too much. Let's change something here real quick. We'll go to what's called leapfrog tracking. So what we'll do is we'll jump ahead of the satellite and see if the satellite goes through the image. It'll jump ahead and then it'll sit for a few seconds, then it'll jump ahead again. Yeah, I don't see it. Well, there's two issues here. One is a skill issue on my part, and the other is the limitations of the scope. It's not really the right scope to do it. You need one that's got a lot wider field to it. So, for example, one of the smaller refractors or that Hyperstar would be a good one to do it as well. Now, one thing that I'm going to try right here is let's stop tracking for a second, because we're right in front of where the satellite would be. Let's see if it goes through the field. Well, I don't see it. Let's see if we can hit it on this one. Yeah, it's eclipsed. That's why we don't see it. Went into the shadow of the Earth. See if we can get it with this one. I think this is one of the Cosmos satellites. There it goes. See it? You see it flash by? Let's check something here. Let's turn continuous tracking back on. See if we can get it with that. There, it just went by again. Sorry about that. Had the screen in front of it. There's the satellite right there. See it? See, the tracking's not perfect. See how it goes back and forth a little bit like that? This is not a cheap mount. It's about a $4,000 mount. But in order to make that a nice, perfectly round dot sitting right in the center, that's a $10,000 or $20,000 mount. So we get what we can get, okay? The bottom line is that wasn't a star because it was moving in opposite directions from the stars. Now, while we're at it, let's just go ahead and have a quick look. Let me just show you Andromeda real quick. While it's slewing over, let me check the... Yeah, rodent. Yeah, I could probably look at, we could probably look for, that Starlink train. We'll do that another time though. So, there is the core of Andromeda. We're a little bit off, as you can see. Let's see if we can bring that up a little more towards the center, and then we'll take a little longer image. See, there's Andromeda right there. Now, this isn't the whole Andromeda galaxy. This is literally just the core of the Andromeda galaxy. And it's a very, very short exposure. So let's go ahead and we'll take a little bit longer of an exposure. I'm going to go ahead and turn tracking on. So here we turn the camera on. There's Andromeda right there. We're going to select a star, and it decided on that one right there. And we're going to start guiding. Now it says it's guiding, and we've got some lines right here, so it's guiding. Now what we're going to do is we're going to go over here to, let's do a 60-second exposure just for fun. That's a half-second exposure, by the way. So let's do a 60-second exposure and see what it looks like. While we're doing that, I'm going to go over here and check this out. Yeah, we're going to have a quick look at Andromeda, and then I'll probably go ahead and shut the stream down for a little while. Because what I need to do is I need to go I need to do some follow-up on asteroids, and that's basically 3-minute exposures of a star field. It's boring as hell, and you do that for an hour. And then you go to another star field and you take a shot, you take 3-minute exposures of that and do another 20 of those. And then you go to a third one. So I'll be up until probably 3 this morning. But I've got to take some pictures of some asteroids. In order to become an official observatory site for the Minor Planetary or for the Minor Planet Center, you have to submit 6 observations of known asteroids. They have to be on each one has to have 2 observations on different nights, and you need to be able to measure their orbits and positions to within an arc second or so. So it's a very demanding thing, and it's a very technical issue. So I've gotten a number of observations, and I'm getting really good results with this software. I'm really nailing the orbits and the positions very nicely. But I have to do the follow-ups to get the second night's observation of them. And, and I have to submit my paperwork to get an observatory number. As it is right now, I've got a provisional observatory, but I'm not official yet. So Shamrock Banks will be an official observatory looking for Armageddon level events. Okay, so now we've got an image here. So let's sit down. Now, you notice that the image here looks all blown out. There's a couple of reasons for that. First of all, this is stretched. It can't be stretched. You don't stretch it here. All right. So what we'll do here is we'll go ahead and put in M31. And we're going to start what's called a live stack. So we've unstretched the image. It's got an appropriate amount of gain on it. 300's good. Now we'll let this image come through, and then we'll stretch it down here, and we should get a little bit more reasonable image. But again, we're looking at the very center of the galaxy. We can't see the entire galaxy. The scope is looking too deeply into it. So let's let this image come out. Okay, so there's the galaxy. Let's go ahead and stretch that. And then we'll make that. So you see here the dust lanes on the Andromeda galaxy. Here is just the core. Now if you want to know what we're looking at, let's go on over here to Andromeda. That's where the telescope is right now. So what we're looking at basically is just this right here. We're just looking at this area. And we're seeing one of these dust lanes right here. So let's go back and look at that. See the dust lane right here? So on the stellarium image, this lower right corner would be up. So if you did the diagonal from the upper left down to the lower right would be up. And now look at it here and you'll see what we're looking at. Okay? As a matter of fact, let's go ahead and look right here. We're going to stop guiding for a second. I think this is M110. Let me shorten this up for a minute. You see, the main Andromeda galaxy is M31. This small one down here that is at about the 5 o'clock position, that's M32. And this one up here that's at 11 o'clock, that's M110. So let's see if we've got M110 here. We're going to stop this live stack. Okay, there's well, I don't know what we're looking at right here, so let's go find out. So let's turn off the camera here. We're going to go down to astrophotography tool, and we're going to connect the camera there. We're going to go ahead and take an image. And while we're waiting for that to cook, we're going to adjust the point craft here to where the telescope thinks it's pointing. Now when we get this image here, we're going to go ahead and hit plate solve and see if it can figure out where it is. Okay, now it knows where it is. We're going to sync the mount to that. Then we're going to go back down here to stellarium. So the mount thought that it was pointing here to this little galaxy, but it's actually pointing over here at about 4 o'clock. So what we're going to do is we're going to move it over to the galaxy. Then we're going to go back down here to astrophotography tool, and we're going to take another image. This is going to be a 10-second image. Yep, it's on it. All right. Notice you don't really see much right here. That's because it's only a 10-second image. Let's go back over here. Let's start guiding again. All right, we're going to start guiding. Then we're going to go back over here. We're going to put the camera back on. And we're going to go ahead and let's put, that's the dark. And here's the flat. Come on. There we go. And now we're going to do some 3-minute images here. And we're going to stack them. Let's see if we can get us a galaxy. Now we'll let that cook for a couple minutes. Hey, Chris Dunham. Or Durham, I should say. Yeah, I played Asteroids as that was kind of my, that and Space Invaders was my game back in the 80s when I was a kid. And that's actually kind of what they look like. So what we're going to do is we're going to image this thing. I'm going to go ahead and put my mic off for a second. I'm going to go have a talk with these dogs who are sitting there growling at each other all the time. You know, they're just pissing and moaning right now, and I'm going to have a chat with them. All right, let's see if we can get an image of this bad boy. Let me get back over here. So we definitely have, you see this big hump right here, we definitely have some images. But I don't see it. See, we got nice round stars now, though. But there's no M100 right here. So, let's go ahead and turn the camera off, see if we can find it a little better. Let's try a different way of finding it. So we'll take an image and we'll plate solve it. Okay, so we're plate solved. Now what we'll do is we'll do a go to. To M110. Try it again here. There we go. That's a little better. Notice it's literally right in the center. So let's go ahead and disconnect the camera again. And we'll go on over here. Well, first, let's go ahead and start guiding again. Now we'll go back over here and we'll try it again. Never said astrophotography was easy, now did I? This gives you an appreciation for the amount of work that actually goes into this. Now we'll wait again. I'll tell you, there's nothing better than sitting here watching paint dry, right? Hey, Ed. Yeah, this is a good place to regain a little bit of IQ. I'm not saying I have much, but I've got a lot more than most of the ones that you see on the Flat Earth channels, that's for damn sure. Gem Panda is actually one of the better ones. There's a good group of people over there, and then they get some really world-class stupidity from the flurfs. And you get some very smart people that try and correct them. But the problem you run into when you're dealing with flat earthers is it's not an issue of a knowledge deficit. It's an issue of trust and conspiratorial thinking. You know, they don't trust anybody and they see conspiracy everywhere, and as a result, there's no amount of evidence that will change their minds. Oh, you didn't see Starlink? Yeah, that's too bad. The thing I'm irritated about is the ISS is going over at 4 o'clock in the morning, and that's past my boomer bedtime. My boomer bedtime is 3 a.m. I missed some nice Jupiter activity last night, too, over on Radio Jove, because it came out, probably half an hour after I went to bed. Let's go see if we've got an image here yet. Not quite. I've got to get my glasses. I can't even read this thing anymore. Well, here's a shock. I don't see my glasses, but we have an image now. Nice round stars. That's good. What you want when you do this on the mids, if you'll notice, this peak goes up rapidly and then it comes down rapidly and then the slope decreases. Then you have this curve that moves when you move the center slide. You want to get that so it kind of intercepts the curve of the data right where it changes slope. Now, that's just one image. That's one 3-minute image. As we stack it, it'll become more clear. Doggone it. See how this is kind of soupy and it's not really nice? Let's go ahead and redo that. But this time with a flat and a dark in it. And you'll see the difference right away. Got 10 seconds until the next image comes out. See how much clearer it is and how even the background is? We'll go ahead and stack a few images there and see what they look like. And while that's doing, let's go see what's going on up here. Yeah, I need a Where's My Glasses app. I can't find them. They're probably right here in front of me. Well, actually, I don't need a VHS to auto-record it because this is live streaming over on Research Flat Moon, and I can just take the slider and go back and look at it. I made some slight corrections in the calibration of the display this morning because I didn't really see those Jupiter storms very clearly. You could tell that they were there if you were looking specifically for them, but they should jump right out at you. No, my glasses are not on top of my head. I do know I spent 20 minutes once looking for my stethoscope and it was around my neck. As a matter of fact, there were 2 of them around my neck. I think I had another one in my pocket too, in my lab coat. There's one more place I can go look. I'll be right back. Okay, found the glasses. Little Missy took them and hid them under the table. I hate cats. Now, the one thing I want to draw your attention to, give you an idea, there's a satellite that went by. You see that? I'm using something called Sigma clipping, and as a result, as this continues to stack, that satellite trail will be erased because it's only on one of the images, and the more images I record that don't have that on it, that'll get dimmer and dimmer until you can't see it anymore. But this is M110. Now, when you come over here to Stellarium, that's M110. Now, if you compare that to the size of Andromeda, it'll give you an idea that we're really only seeing a tiny portion of the center of Andromeda when we looked at it earlier. We need a telescope with a lot less focal length to see all of that galaxy. As a matter of fact, sometimes it's even better to just use a camera with like a 300 millimeter lens on it. But this small galaxy up here is taking up almost the entire frame. That's just this galaxy right here. So that'll give you an idea of the amount of magnification that we're looking at right now. And again, we're only looking at about 25% of what the telescope can do. Yeah, that satellite streak will go away in a little while. That's the problem that you run into nowadays. There's so many satellites up there. It's very difficult to get long-term images without at least one satellite trail in it. And when you're looking for the asteroids, I like to turn off the sigma clipping. So I actually have to throw out an image that has a satellite in it. The problem you run into with sigma clipping is it looks for differences between images and then de-emphasizes those differences. And what you're doing when you look for asteroids is you're looking for a small moving object in a stable star field. Sigma clipping would reduce the intensity of that little moving object and make it harder to find. The other thing that I do too is I generally turn off what they call dithering. It's off right now, but occasionally when you have dithering on, that's one way to decrease the amount of noise in a signal. You know, if you look at the graininess in the background of space, that's noise. Now, you combat that two different ways. One is you use a cooled camera, which is what I'm doing right now, to keep the camera from getting too hot and generating noise. The other thing that you can do is something called dithering, which means that you'll take 5 images and then the camera will stop taking images, but shift over slightly. It'll shift the telescope just a few pixels, and then it'll start taking images again. And after it does that a few times, what happens is you tend to average out the noise a little better, because you're not looking, you know, the camera's not looking at exactly the same spot all the time. That also decreases dust motes and it decreases hot pixels as well. But we're combating dust motes and hot pixels with the dark and the flat frames that I took at the start of the session. Well, orbital telescopes, yes. For example, you know, we'll take a couple more images here, and then I'll shift over to Jupiter, or better yet, I'll see if Saturn's still visible. And you'll see some of the problems that you run into trying to take a picture of a planet, for example, through the atmosphere. First, you need a very long focal length to get a good picture of a planet because they are very tiny. You know, compared to a nebula or a galaxy, a planet is just a grain of sand at great distance. And second of all, you get a lot of shimmering due to the jet stream and atmospheric winds. It'll cause a miraging and a shimmering of the image, and that just really cuts down on the detail. And you can kind of correct for that to some extent using a technique known as stacking, where you take 10,000 images of Jupiter, you take the clearest 10% of them, and then you stack them one on top of the other, and you can bring out some nice details. That's how you get the nice pictures of the red spot and everything. But just looking at it through a telescope, it looks blurry. Sometimes you can make out some banding. You can put a filter on it, say a red filter on it, and try and emphasize some of the banding a little bit. But taking pictures of planets is very challenging, and the people that are good at it, my hat's off to them. Now, as far as us putting orbital telescopes up, there's no real need for a hobbyist like me to put an orbital telescope up, but there may come a time that we have some small telescopes up in orbit that I could buy time on, for example. For $50, I could have access to the telescope for 3 hours. And, the nice thing about that is you can do it day or night. It doesn't really matter. Now, I do have some other really cool things that are going to be coming up as far as astronomy. For example, there's a YouTube creator down in the Sydney area by the name of Where's Wally. And Where's Wally is also an amateur astronomer like me who knows how to hook his telescope up to his computer. Well, the cool thing about that is I can turn my computer over to him and he can run my telescope. So he can have a look at stuff in the northern hemisphere that he wouldn't otherwise be able to see. And by the same token, in the middle of the day, I can log on to his computer and I can take control of his telescope and I can look at, a lot of the stuff down in the southern skies that I'll never get to see. So stand by for that. That's something that'll be coming up in the not too distant future. He's a good guy. Another one that does that I've known for years is Wolfie, and I may be able to take over Wolfie's. Wolfie does a lot of satellite work with Himawari and things like that. And I may be able to take over his telescope once in a while too. Now, we do have an event coming up here at the equinox towards the end of September. And that is that these geostationary satellites will become eclipsed as they go through the shadow of the Earth. And we may be able to try and get some observations coordinated between Michigan here in the U.S. and Australia, both on the Sydney side and over on the Perth side. And we may be able to do some interesting observations, some simultaneous observations. I got to time it right because there's a very, very short window where it's dark here and it's dark there, Yeah, Where's Wally controls Wolfie's telescope, and Wolfie plays with Wally's telescope as well. I'm going to be in that little mix. Now, Wolfie is kind of interesting because he's got a lot of exposure to the northern hemisphere. He's up here quite often, and he generally brings a small refractor with him as he goes. So he'll make observations from the Middle East. He'll make observations from the United States here. He's in Texas quite a bit. He's in Hawaii. So he gets to make observations all over the world. Where's Wally's mostly in Australia. I'm, of course, in the United States. Let's go have a look at this thing, see what we got. See how that satellite streak is getting smaller? The Sigma clipping I don't think is on right now, is it? No, it is. So Sigma clipping is on. It's kind of a neat little picture, isn't it? Well, what time is it? Well, it's 12 midnight. We've been at this for about an hour and 40 minutes. Is there something anybody in particular wants to see? If not, I think that we're probably going to go ahead and shut this down. Let me just have a real quick look and see if there's anything interesting in the sky. Trying to think of what time Orion... Oh, I wanted to show you... Let's go ahead and turn off tracking. See how nice, look at this tracking. It's all in that center ring. And look at how flat this tracking is. This is a really nice mount. But in any event, let's turn that off for a second. And let's go ahead and end this. Now what we're going to do is we're going to drop our time for our exposure down to about 1/4 of a second. And I'm going to head on over here to Saturn. I should still be able to see that. I don't think it's behind the trees yet. I've got trees to my southwest and my west, so I'm kind of limited to 40 degrees or higher. And there's Saturn. Now, what we're going to do is we're going to increase this up to 100%. Now you can tell already. You see how it's pulsating a little bit? That's the jet stream and winds causing issues. So let's get on over here. See if we can get an image here. Start decreasing the exposure time. And that's probably about the best that we're going to be able to get. Now you see a hint of the Cassini division right here. You see that dark line? And you can see some banding in the clouds. But you see how it's just jumping around? That's the effect of the atmosphere. Now in space you won't have that. Now the other thing that you'll notice is if you adjust your exposure so you can see some detail on the planet, you can't see anything else. But let's increase the exposure and see if we can see the moons. There's a moon right there, I think. Yep, there's Titan right there. Down at about 5 o'clock. And now we're starting to see some of the other moons. See the moons? But look what happened to the planet itself. It's all blown out. Now, if you want to know what those are, see, here's Titan right here. And that's Titan down here. And then you've got 3 more right here. up by the planet. There's a fourth one right there. Right at 11 o'clock at the disk of the planet, you'll see there's a tiny little bulge there. That's another moon. See if we can bring that up a little bit. See, there's another moon right there. There's Titan. Now, there are some telescopes out in the amateur world that you can actually image Titan with. And let's just see whether or not we can get any detail at all out of Titan. Now, if you get a little bit larger, you might actually be able to see some detail on Titan, but this telescope's simply not large enough to do that. Show you a couple of the other planets real quick. So we'll go over to Jupiter. There's Jupiter. See here are the moons. Got Io and Europa and Ganymede and Callisto. Those are the Galilean moons of Jupiter, the four of them right there. And again, if you look here, you can see them listed right here. So this is Ganymede, and there's Io and Europa and Callisto, and you can see them right here. Ganymede, Io, Europa, and Callisto. And once again, to see the moons, Jupiter's all washed out. But let's go ahead and fix that. See, we're starting to lose the moon, but but Jupiter's not quite as washed out. And there you see Jupiter. But notice it's dancing around a little bit. It's a little more stable tonight than I've seen it. But you can see some of the banding in Jupiter. But look how it's just shimmering. See what else we have. Mars should be up now. Maybe not. Oh, Mars is just coming up. It's right there. We might not be able to see it. It may be too low on the horizon. There's an island and some trees right over there. Yeah, it's behind the trees. Well, one other thing that we can look at is something called the Pleiades in Taurus. The Pleiades is also known as Subaru, and it's M45. So they're called the Seven Sisters. And in the east, they're called Subaru. And in the west, they're called the Pleiades. But even something this size is too big for the telescope that we're using tonight. So what we're going to do, take a 15-second exposure real quick. You see, this is what happens when your equipment works right. You know, to be honest with you, the LX200, hey Sean, the LX200 is a really good visual scope. That's the Meade, the 10-inch Meade that I was using. But the mount that it is on is an alt-az mount, and even when you put a equatorial wedge in, you just really don't have the control over it that you need for long exposure astrophotography. It's designed primarily for looking through it, you know, looking through an eyepiece. And, you know, it just was not suitable for what I wanted to do with it. So I sold it to a friend of mine, and I bought this mount, and I've got a good sized telescope on it right now. I've got a much bigger one coming in the next couple of months. But it's really, it's going to really improve the astrophotography that I do. And it's going to make these live streams a lot more enjoyable, because it's not fun screwing around and just messing around with it. I think it's M45. So what we're going to do is let's go ahead and do a couple of 3-minute exposures on this just for shits and giggles. Well, that's running. Let me go see what's going on over here. Well, Sean Hawkins has joined us. Sean is a really good guy out in California. I've had a lot of dealings with him. I actually bought a telescope from him not long ago that I've been very, very pleased with. Didn't really care for the mount, but the telescope has probably got some of the best optics that I have. And it's one of my favorite telescopes now. I've got it on a good mount, and that really makes a big difference. That's the main telescope that's out on the tree stump mount for those of you that have been following along. So that's going to take a couple of minutes to do. We're going to do a full 3-minute exposure on that. And we've got lights and darks on, so it should be pretty good. But I'll give you an idea that, you know, I can't get the entire Pleiades in. And there's a gas cloud between us and the Pleiades that they used to think was actually around the Pleiades itself. They thought it had some nebulosity there. But in reality, that cloud is between us and the Pleiades. The Pleiades are on the other side of it. So it's kind of an optical illusion. Yeah, Eric Dubious would, you know, they've already denied these things. You know, I was over on one of the chats the other day, and I said, yeah, and by the way, you know, they were saying, oh yeah, well, yeah, Artemis is launching this weekend, because I pointed out the fact that they were losing some of their arguments. For example, you know, when they say that we can't leave low Earth orbit, well, we're doing it this weekend. So that's going to wreck that. It's going to wreck their argument about the distance to the moon. And they said, oh yeah, and we're going to have all sorts of excuses as to why we can't see it from Earth. And it's, well, funny you should mention that, because I'm actually going to track it. And I'm going to image it from my backyard on the way to the moon and on the way back from the moon. One of the things I'm going to try and do tonight is get a picture of the James Webb Telescope, which is a lot farther than the moon. It's 1.5 million kilometers away, I think. And, you know, the moon's, you know, that's 1/5 the distance to the moon, roughly. Or it's 1/5 the distance to the moon. So if I can see the James Webb Telescope, I should be able to see Artemis. I'll have moonshine that's going to interfere with it. But I should be able to, you know, on the way to the moon, of course, the moon's not going to be in the background. Oh, you know what I forgot to do? Forgot to start tracking. But here are the Pleiades right here that you can see. Now the focus on the guide scope is not very good, which is why the stars look a little fuzzy. But that's not for imaging, that is for guiding. And as long as I've got a star that I can see, like that one, I can guide on it. Well, that gave me an image. That looks like it was a combination of a few images, so we'll get a fresh one here with guiding. Oh, we have a few viewers out here tonight. Are you guys enjoying this? Is this something you would like to see more often? I don't mind doing these. You know, I'm doing them anyhow. If you want me to share it with you in real time, I'm more than happy to. But, you know, I mean, if it's something that you enjoy, I'll do it. Well, the battery's charged up finally on this laptop. I'm going to go ahead and take it off of low power mode. And that should help a little bit. Well, another 40 seconds. We'll have an image. But these are the Pleiades right here. So that'll give you an idea of the size of it. They're part of the constellation Taurus. Now, there's a red star here. Mars is directly above it, and the Pleiades are directly above it. So it's kind of very interesting to look out to the east in the evening right now, because you see a really nice display. Now, one thing that's coming up that won't be for several hours is our favorite constellation right here. There's Orion, and there's the Great Orion Nebula. That will come up in a few hours, and I'm going to try and get an image of the Orion Nebula tonight because I've been aching to image it. It depends if I'm still up around 3 or 4 o'clock in the morning. You know, that's a winter constellation, and it doesn't come above the horizon at night until mid to late fall. So it's starting to come up in the early morning hours now, and it'll be up in the evening in 3 or 4 weeks, you know, in a more reasonable hour of the evening. Okay, so this is the Pleiades. And as you can tell, we can't really see all of it. So you see you've got the bright central star, and then you've got this triangle of stars right here. Let's see if we can spot what we're looking at. So here we go. So I see a triangle right there. Let me look at it again. There it is. So here's that bright star, and you see that little cluster of stars right there? And then here's the triangle that we're looking at. That's all that we can see out of that whole group. About this, just the central core here. We can't see this whole cluster. Well, guys, I think that's probably enough for tonight. I hope you all enjoyed yourself. I had a lot of fun doing this. Missy had a lot of fun irritating me the entire time by trying to jump on my keyboard and knock over my soda and hide my glasses. But we made it through it. Didn't have a single problem with the mount, as you can see. Telescope's working beautifully. That's going to be the way it's going to be from now on. Where, you know, the time that, you know, I spend the entire time trying to troubleshoot the telescope by trying to make it do something that it wasn't designed to do are over. I've got the equipment that I need to do this properly now. So, and a nice fast computer to run everything. So, this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for joining me for a couple hours.